Hey guys, so welcome back. Last time we talked about product and quotient rule, and likely we discussed some other things in class as well, maybe related to instantaneous rates of change versus average rates of change, secant lines versus tangent lines, things like that. And with the product and quotient rule, I told you I didn't actually supply any sort of proof for those rules. And like I said, I'm not going to supply proofs for a lot of different things because obviously in Calculus 1 or first semester AB, we don't have necessarily the time to do that. But what we're going to do today is we're going to look at trig derivatives. And I have to say almost all the trig derivatives, because every trig function besides sine and cosine can be reduced to sine and cosine, are going to be sort of tied back to some of this original math here. And so we are going to run through the derivation for sine and cosine together so you can see how they're formed. Now, I have to say usually in class after doing sine, I force you to do cosine and then figure it out for tangent and whatever else. I'm not sure I'm going to have us do that because obviously you're not here right now. But what we are going to look at is this sort of derivation. So let's say we have f of x equals sine of x, right? This obviously is a polynomial. We can't use power rule. It's not a constant. It doesn't reduce to zero. And so how are we going to deal with it? Well, we're going to deal with it using the first definition of a derivative. So the first definition of a derivative, as hopefully you know, is the limit as h approaches 0 of f of x plus h minus f of x all over h. I stated that we use this in the past, specifically when we're trying to find the derivative for a function generally rather than at a specific point. And so we're going to have to use that here. If we plug in or utilize sine as our f of x, we're going to get a limit which looks something like this. So we'll have the limit as h approaches 0 of the sine of x plus h minus f of x, which is the sine of x, all over h. And when we did this with polynomials, what was nice is that we could just factor out the h somehow and then cancel the denominator and plug in 0 for h. I think that you can see pretty clearly that that's not going to happen here because there's no factorization of h which can be done here. And so what we're going to have to do instead, as many of you might guess, is to use some trig identities in order to figure this situation out. What we're going to use is an angle addition identity, which may or may not be familiar to you. So if you have the sine of one thing plus another, it can be expanded. It specifically can be expanded like so. We could have the sine of x times the cosine of h plus the cosine of x times the sine of h. This is the angle identity I'm going to use, and I'm going to expand this now using that. So we'll have the limit as h approaches 0 of the sine of x plus h, which is the same thing as the sine of x cosine of h plus cosine x sine of h minus sine of x all over h. Cool. So all we did there was substitute in that angle identity, and now we've rearranged it to some degree, or not rearranged it to some degree, but rewritten it. So that said, I'm thinking ahead. What we are going to do is we're going to rearrange it slightly. And as I go through this, you might sort of be keen or think about why I'm doing this in the first place. Let's go ahead and do it. I'm going to take this sine of x and move it next to this piece here. So I'm going to have sine x cosine h minus sine x. I'm rearranging my numerator. And after that, I'm going to have my plus cosine x sine h. I'm also going to split up this entire addition into two separate fractions. So the denominator is still the same here, common h, but I'm just going to split up my addition and subtraction separately. So I have this fraction here and this fraction here. So why am I doing that? Well, you might see why I'm doing it. Maybe you don't, I'm not sure. The reason why I'm doing it is because there are some special limits which are sort of making themselves clear here. I want to factor a sine x out of the top of this limit. So I'm going to have the limit as h approaches 0. I'm going to factor a sine x out. That's going to leave me with a cosine h minus 1. Of course, this is over h currently. And then this second fraction, I'm just gonna write as cosine x times sine h over h. So maybe you see what I'm doing here, maybe you don't see what I'm doing here, I'm not sure. But if you don't, that's okay, you'll see soon enough. I've grouped these things together in such a way because there are some special limits which I've produced, right? There's the sine of h over h as h approaches 0. There's the cosine of h minus 1 over h as h approaches 0. Maybe you remember what those are equal to, right? We've definitely dealt with the sine of x over x as x approaches 0 many, many times, and hopefully you remember that limit proceeds toward or is equal to 1. This one, which is a little bit less common, you may have forgotten, but the cosine of h minus 1 over h as h approaches 0, or more commonly how we write it, the limit as x approaches 0 of cosine x minus 1 over x. That proceeds to or is equal to 0. The fact that it's equal to 0 and is being multiplied times the sine of x means this entire term here is going to cancel out, right? And then in this case, as that thing proceeds towards 1, it essentially reduces this entire limit to the limit as h approaches 0 of the cosine of x. This is, of course, just equal to the cosine of x, right? That limit is defined by h there, so that's not going to be plugged into the x if that's something that you're thinking. And so we come to the conclusion then that our solution, or the derivative of sine of x, is equal to cosine of x. So we started with f of x equals sine of x. What we really did is took the derivative, found f prime of x, and that conclusion that we came to is that it's equal to cosine of x. So you might most likely be thinking, am I going to be required to do this? And sometimes I have to say I have required people to do it at least once for sine or cosine on a test or some other quiz or whatever. In general, however, what you're going to need to have memorized is the fact that the derivative of sine is cosine. That's maybe the most important part. That said, this procedure is quite useful and necessary for doing these types of derivations. Now, normally in class, what I have you do is go ahead and perform the derivation for cosine. That is, you can take cosine, plug it into the first definition of a derivative, and then utilize that angle addition identity, which I just put forward, but for cosine instead. I'm not going to do that here, but if it's something that you're interested in doing, just take note that the cosine expansion of x plus h is a little different. It's cosine x cosine h minus sine x sine h. That said, the solving of that procedure is extremely similar. You're going to still push things together, rearrange, and factor so that you can produce those special limits. And in the end, what you end up showing is the derivative of cosine. And so let me just list that out now. If you have, for instance, f of x equals cosine x, its derivative, f prime, after you follow the procedure that we just followed, is negative sine of x. And that's necessary, obviously, to have memorized. What we just concluded a second ago, right, was that some g of x sine of x, when you take its derivative, or g prime of x, is cosine x. And these two are extremely important. And then if you wanted to go on and look at tangent and all those other things, you could totally do that, and you should do that to some degree. But I'm just going to list them out currently so that you just have a clear list of each of these things. So I'm just going to maybe make a table of something. Let's say function, and let's say its derivative. So we've got sine x, we've got cosine x, and negative sine x for its corresponding derivative. Obviously, we're going to have tangent x. Its derivative is secant squared of x. And then, of course, we've got, right, the reciprocals of all of these different things. So let's go ahead and list those out. So we've got cosecant, we've got secant, and we've got cotangent. And their corresponding derivatives are negative cosecant x cotangent x. Secant's derivative is secant tangent. And then cotangent's derivative is negative cosecant squared x. So this is a table that you're 100% just going to have memorized. Now, you're going to do enough of these problems in practice to not necessarily have to explicitly memorize them, but they are things that you just need to know. And as I said, the derivation for them are actually not too difficult. You're simply going to be following the procedure that I just did for sine and then utilizing probably some slightly different angle identities in the process. All right, so now that we've got that down, let's look at just some examples in which we kind of tie together these things with some of the stuff that we've done in the past. So let's just take some random function here. Let's say the function is, I don't know, h of x equals, let's say, secant of x divided by, I don't know, minus cosine x. So here's our function, and let's say it asks us to find something. Let's say it asks us to find a tangent line to h of x at x equals, let's go for something interesting here, I'm not sure, x equals pi over 4. So find a tangent line to the graph, you should find a derivative, right? We should find h prime of x. This is a fraction, yeah? So if a fraction is present, we obviously need to use quotient rule. If you've forgotten what quotient rule looks like, remember that it looks something like this. You've got a function on top and a function on the bottom, and its derivative is g of x, f prime of x minus f of x, g prime of x, all divided by g of x squared. Denominator, numerator's derivative minus numerator, denominator's derivative all over denominator squared. Going quick, but you've got that written down somewhere. All right, let's do the evaluation. So we've got denominator times numerator's derivative. What's the derivative of secant x? Well, secant tangent. I know that now. You'll know that soon enough. Minus numerator, secant x, times derivative of the denominator. What's the derivative of the denominator? Well, derivative of 1 is just 0. That's a constant. Derivative of cosine is negative sine, but there's a negative there, so this is going to be positive sine. And then all of this is divided by denominator squared. Why did I switch to orange? Oh, because I did that over here. Okie doke, so there's that. That said, are we going to simplify this? No, I'm not going to simplify it. The reason why is because it tells us to evaluate it at a specific value for x. So I'm going to find h prime of pi over 4, which means I'm going to plug in pi over 4 to this thing and see what happens. Pi over 4, hopefully you recognize, is a 45-degree angle. In this case, and I'm assuming that you recognize what your trig values are and evaluate trig values. We'll have a cosine of pi over 4, which is root 2 over 2. The secant, which is the inverse of cosine, 2 over root 2, times the tangent of pi over 4, which is a lovely 1. Secant of pi over 4, 2 over root 2. Sine of pi over 4, root 2 over 2. 1 minus cosine of pi over 4, root 2 over 2, square that. Now, it's probably worthwhile to go ahead and figure out what this value is. The reason it's worthwhile is because it asks us to find a tangent line in the first place. So we're going to have to find this particular value. I can see that those are going to simplify and become 1, so that's good. That's nice for us. Is this going to simplify and become 1? No, it's not. We're going to have, in this case, 1 minus root 2 over 2 times this thing. I think it's worthwhile to push this stuff together. 1 obviously is the same thing as 2 over 2 to make a common denominator. So that's going to give us 2 minus root 2 all over 2 times 2 over root 2 minus 1 all over 1 minus root 2 over 2 squared. A little bit more simplification is going to happen there. That's going to leave us with 2 minus root 2 all divided by root 2. And then we've got this wonderful situation here. It's probably worth it to FOIL that out really quick. So we've got 1 minus root 2 over 2, 1 minus root 2 over 2. What's that going to give us? 1. That's a minus root 2 and another minus root 2. So minus 2 root 2 over 2's. And then those multiplied together are just going to give us a positive 2 over 4, or 1/2. Those are going to cancel. 1 plus 1/2 is 3 over 2 minus root 2. Fun. And then for the sake of saving myself time and not doing much more of this, I am just going to calculate the value of this quickly using a calculator. Because I've started to lose patience with the simplification. All right, so hopefully I've done this correct. We're getting a value somewhere around 4.8284. 4.8284, what is that? That's the slope of the tangent line, right? That's h prime of pi over 4, yeah? Now, I chose random numbers here, which is why this turned into such a nasty situation, but I still think it's worth our time. You'll notice, however, that I'm not actually done with this problem yet. The reason I'm not done with this problem yet is because it asked me to find a tangent line. It did not ask me to find the slope of a tangent line. It asked me to find a tangent line. So how am I going to find a tangent line? Well, any line that I ever want to find is going to involve finding two things, right? It's going to involve finding a slope, using a point, and then using point slope form in order to calculate the equation. So I just found the slope, right? I'm stating, let's see what this green looks like, that the slope is 4.8284. I need a point. Well, the x value is pi over 4. Do I have a y value? No, I don't, but I can find it, right? I can just plug in pi over 4 to h of x. Find h of pi over 4, that's going to be the secant of pi over 4, which is 2 over root 2. Cosine of pi over 4, root 2 over 2. Let's do just a little bit of simplification. This is the same thing as, let's just back that up. 2 over root 2. On the bottom, if I put a 2 here, that's going to be 2 minus root 2 over 2. Let's see, did that help at all? I don't think it did. Let's flip and multiply. That's going to give us 4 over root 2 times 2 minus root 2. If you didn't hate me before, you probably hate me now. 4, 2 root 2 minus 2. So this is our y value, wonderful. 4 over 2 root 2 minus 2. Making myself suffer for this one. Let's go ahead and find the equation of this line using point slope form. We've got y minus this wonderful thing equals our slope, 4.8284. I hate the fact that I have fractions and decimals going on. That times x minus pi over 4. I'm going to accept that as my final answer so that I don't kill myself in the process of doing these problems, but note that obviously we could have done that just a little bit differently. All right. So what did we do there? Well, we covered a quotient rule again, and we used a couple of different trig functions in the process. One last thing that I want to make clear about trig functions that's pretty interesting before we go is the fact that trig functions can be kind of special in that they cycle. Let's take f of x equals cosine x as an example, and let's just go through the first few derivatives of this thing. Let's see, so if we were to find the first derivative f prime of x, I think we concluded that was negative sine of x, right? All right. What about if we take another derivative or find f double prime? The derivative of a sine is cosine, but there's a negative out front, so this would be negative cosine, right? I think we're on to something. I'm, of course, talking to myself looking at the screen, but you know. Derivative of cosine is negative sine, right? But negative sine times a negative would be positive sine. Okay, I think we're doing all right. Now we're going on to the fourth derivative. Derivative of sine, what's that? Well, that's just cosine, isn't it? Well, that's interesting. It looks like we've gotten back to cosine. Isn't that correct? Yeah, so what's interesting about this one, and this will occur obviously with sine as well, is that the thing cycles. So not that I think I've seen a problem similar to it, but it's interesting to note. But let's say you were asked to find, for instance, like a derivative way down the line of cosine. I don't know what it might be, but let's say it'd be like the 25th derivative of cosine. It's not going to be worth your time, obviously, to sit here and do 25 cycles of this. Instead, it's probably worth your time to just recognize what pattern is going to occur and where you're going to end up for each of these things. So obviously, every 4 cycles, right, or multiple of 4, you're going to end back at your cosine, correct? So in other words, I believe, if that's correct, that the 24th derivative, right, which would be 6 times 4, variation of 4, that should be equal to cosine of x, correct? If I'm correct about that, then the 25th, or next one, would just be the derivative of cosine, which is negative sine of x. Hopefully I'm correct about that. I'm doing this off the top of my head. I think I'm correct. But this is a little bit useful to recognize that it's a pattern which could be helpful, perhaps in one of the homework assignments that's coming up. In any case, that's the sort of basic introduction to these trig derivatives. And I have to say that for this section, really what you're going to end up doing is just memorizing all those trig derivatives that we put down in the beginning. But I do think that this procedure and these problems will be helpful overall for your fluency.